Hey guys, so I think we're gonna get started here. So, welcome to our first GBM, at least the IREC team's first GBM. So we are a team competing in the Intercollegiate Rocketry Engineering Competition, or IREC. If you can, please scan that QR code so that you can so that we can give a quick survey and make sure that you came to the GBM. We got some announcements before we get started. So on next Wednesday, we have a general education meeting with Alex Sanchez-Aria. He's our avionics and recovery lead. It's a great, I think general education meetings are a great way to get like caught up to date on all things rocketry, and it can help you a lot. Alex, if you have any updates you want to give on that.
Sure. Can you guys hear me okay? I know my internet is not that
Yes.
great. Okay. Basically, what we'll be going over in the meeting is basic rocketry, like the components of what it takes to build a rocket. In terms of the airframe, different methods of like ejection, deployment, recovery, and how basically the aerodynamics of the rocket, and then an introduction to how Open Rocket works and the software we use to simulate stuff within our competitions. The majority of the leads use it to simulate and test before we build or do anything with any sort of rocket. So I think it'll be a really good, important meeting. Sorry for the squeaking, that's my dog in the background, but important meeting. And for anyone who wants to develop their knowledge and bring it to the table for their given sub team, then for sure join, and then that'll help you later on for other stuff in case like you want to apply for a certification and stuff like that.
So next we have the payload experimental lead position is still open. We'll have more details about that later in the meeting. The form is in the general channel on our Slack. So if you want to get started on signing up for that, it's available. We also have a t-shirt and polo sign up on that QR code right there. Hurry up, I guess, because Mika wants to submit the order. Okay, so a little overview of our competition. So we are competing in the Spaceport America IREC competition. It's the world's largest university rocketry competition. 1,700 students from more than 150 teams compete. They all go to a big open field in Las Cruces, New Mexico, and it'll happen about summer in June. So the thing that separates us from NASA SL and other rocketry competitions is it's basically the design is basically entirely open. It allows us to really flex our creativity. We can pretty much do or look into whatever research or whatever aspect of rocketry that we want to go into as a team. The mission is simply to deliver any experimental payload, and that's completely up to us what that experiment is. So we are competing in the 10,000 feet category at 10,000 feet and COTS motor, or basically a consumer off-the-shelf motor. You didn't build it yourself, you bought it. This has the entry category for us, and we're hoping that with our development, our propulsion team, and just overall success, we'll start going to 30,000 feet and making our own motors. So here's a couple of pictures. You can see it's a huge amount of people all going out to just like a field and flying. On top of this, there's like a hotel and whole experience. So this is basically like a paid trip by the university for a bunch of us and you potentially if you join our team. I think it's really exciting, but first off, before we get there, we need to build the rocket. So there's a lot of work that goes into that. So here's our organization structure right now. I'm the project manager, and below are several leads with different sub teams. Essentially, as a part of this team, you would work under one of these sub teams in a specialty such as structures, avionics, flight dynamics, recovery, something that you want to look into or something that you're interested within either rocketry or your major. Doesn't necessarily need to be an aerospace major. That's something that we're really looking forward to, is finding new majors that can really spice up the team and really give us like a diversity of opinion and expertise, because as of now, we're mostly aerospace, mechanical, industrial, and some industrial and chemical engineering majors. But really, a rocket it seems like an aerospace thing, but really it's a test bench for all these different majors. So there's a lot of different specialties that goes into building a rocket, and potentially you can fit into there. So let me talk about our rocket right now. So our last rocket kind of exploded. So we're building all from scratch. The target altitude is 10,000 feet. The experimental payload has a certain requirements from IREC. The weight must be greater than 8.8 pounds, and it must be in the CubeSat format. CubeSat is a 10 by 10 by 10 centimeter cube that's typically used to standardize satellite launches in space. And IREC is kind of incentivizing using the CubeSat format. The CubeSat can be ejected from the flight of the rocket. So it could be deployed on a parachute or on the line of our parachute or a rocket. So it can be exposed into the air. It doesn't have to remain inside the aircraft. And it must conduct some type of experiment. Some people have done biological experiments where they've measured the growth of bacteria on a petri dish. One of my ideas was to measure cosmic muons or cosmic rays via muons. We can get atmospheric data, all types of things. And this is where the really that all majors aspect really fleshes out is in the payload. And we're looking for someone to do the payload, so please apply to that form. So the motor that we're flying is an M-class motor. A motor is basically a rocket engine. It carries 10,240 newtons of thrust. But that's basically the 2 classes under the legal limit. So we're kind of getting close to as much as you can do legally as a private citizen. Another goal or another requirement is that we successfully recover the rocket without any structural damage. AKA, you'll be able to refly it in 2 hours with minimal repairs necessary. And it must be flight ready on the pad for 2 hours. So all electronics and systems are armed and ready to go for 2 hours. And it also requires a GPS system to locate the rocket and redundant avionics to make sure if one flight computer fails, the sequence can still go on with another electronics. So let's go over our current flight vehicle. Right now we have an apogee of 10,122 feet, a maximum Mach number of 1.0, a length of 8.19 feet, so a little bit taller than a person, a diameter of 6 inches, and a motor. The motor is an M2000R. The 2000 designates the average thrust of the motor. We have a static stability margin of 2.57 calibers. These are all things that don't really make sense to you now, but if you are part of the flight dynamics team, it really rings a bell for you. So let me give you a quick overview of how, if you are new to this, how rockets work, at least student rockets. So powered by the motor upon ignition, which is just simply from a spark supplied by a battery, the motor ignites, the chemicals react, and the pressure builds up and propels the motor up. Newton's second law, or third law, sorry. Equal reaction creates an equal force. So it first ignites for about 5 seconds and then shoots up really quickly. But then for the majority of the flight, it's unpowered flight, or basically coasting through the air until it gets to its apogee. Once it gets to the apogee event, or basically the tallest or the highest point in its flight, the avionics or the flight computer inside the rocket will detect that it's at that point, or that it's now decreasing in apogee or altitude, and will fire a firecracker or a black powder charge to basically pressurize the vessel and pop open the rocket and separate it into 2 parts. That allows the parachute to deploy and to slow down the rocket. So for model or high powered rocketry, we usually do a dual deploy setup where we have a smaller parachute that deploys at the apogee event. And then when the rocket descends to a lower altitude, it'll deploy a better main parachute so that the rocket can slow down to a safe descent. the whole purpose of this is to prevent the rocket from drifting away under that main parachute if you're to deploy at apogee. So this reduces how far the rocket goes. So with the IREC competition, there's some new things that we can do to the events that go on in our rocket. One example is this team on the right deployed a parachute, sorry, not parachute, payload with a camera on it from a parachute. So you can see after the ignition, the flight of the rocket gets to apogee, the payload actually separates from the vehicle, and the rest of the vehicle descends on a drogue, simple dual deploy setup. The payload, however, has its own parachute setup that allows it to take pictures downrange as it descends to the ground. So that's one example of something that we can do where we deploy the payload on a parachute. We can also have the payload hang on the parachute line that connects to the flight vehicle. So that's another option to do. It really depends, and that's where the freedom of design really comes into play in IREC. So I'm going to give you a quick summary of our goals. So the first goal that we have really is just to win. We want to do our best. There's many ways you can win. You have an overall team place, but there's also some awards and specialties such as modeling and simulation, flight dynamics, team innovation that your team can be awarded on in that. Also, there's a presentation panel that you can give to a panel of scientists on a specific aspect of your rocket, and that's another form of recognition. So it's a great place to do some research on either aerodynamics or whatever specialty you want to really flourish into. Some design goals. So I personally really want to hit that 10,000 feet target altitude. It's something that we've tried to do on ESO, and it's something that I think it's a great mission to pursue in IREC as well. Most importantly, though, we want to have a more robust and reusable rocket. My goal is to have a rocket that can fly basically every month if possible, which is possible with these type of rockets. It's just very hard. And finally, we want to try to orientate the rocket using an active control system, which our ACS leads, Tispan and Willer will give you a summary on feature in the later of the presentation. Some goals within our team are to conduct a meaningful engineering research within our specialty. Basically, just start really looking to what we want to do as engineers in the future, like whatever specialty you like. Try to pursue that now and use the rocket as a test bench for that. So I think it's a great way to start off on your graduate career. Some ways we're trying to do that is to submit our work to student conferences or as our honor thesis for our magna cum laude. We also want to make contacts with our alumni in industry itself, so that we can start using this cool tech for our systems. We also want to start developing experimental subsystems for swamp launch. Our rockets are fairly simple now, but we can develop some really cool subsystems that really expedite the process or robustness of the rocket entirely for us. And we also want to pave the way for a new IREC team to carry on the progress that we've made this year and provide guides and documentation for researchers or rocketry enthusiasts online to also use. All right, so I'll leave it to Tispan and Willer to give a quick summary of our ACS design selection. Go ahead, guys.
So I'm Tispan and I'm working on the ACS this year with Willer. So first of all, what is an ACS? ACS can stand for a lot of things, but right now for us, it stands for Active Control System. Last year, we had a altitude control system, which were deployed drag blades near the center of gravity of our rocket. And the purpose of that was to slow down our rocket when it was in coast so that we could hit our target altitude, one of the goals that Bilal mentioned earlier. We discarded this because after speaking with Dr. Lin, we think that it's not the best way to go about it because the drag blades. They take away velocity, but when you're in coast, there's really no way to increase the velocity if your control that you sent to the drag blades was incorrect and it overshot, and now you're below your target altitude. So our attempt at fixing this is with orientating the rocket instead, so that we can have better simulations and that our rocket will follow our predicted flight path more accurately. So in our design selection, there's many ways we can choose to orient our rocket. We're choosing canards, which will create a control surface and angle our rocket. But there's other possibilities, such as with gas thrusters, which you might have seen on the space shuttle or on other space vehicles, which just basically shoot compressed gas to orient our rocket. Vernier thrusters, which will be near bottom of our rocket, near the motors, and it's on the Soyuz, and they're basically little rocket motors that you can orient as well. And then there's gimbal thrust, which if you've ever seen a thrust vector control, it's basically gimbaling your main motor so that it angles the thrust when it goes up. But we're going with canards this year. So when you want to make a control system like this, there's really just 3 steps. The first step, which we're working on right now, is the design phase. We want to figure out how we want to control our rocket and what sensors we're going to use to measure the behavior. And then next step is to figure out the electronics we're going to use, what motors, what sensors, and how you're going to get the data from that. And the last step is the controls, how you want to close your feedback loop and how you want to choose the gains to affect your control system. So the first step is the design phase. After our latest meeting, we've figured out the equations of motion of the rocket, which you can see below. Basically, it's a moment balance equation, and we're using the lift from our canards, which you can see an example of on the right, and that will affect the moment centered around the center of gravity of our rocket. Right now, we're working on implementing changes into our MATLAB simulation. This includes a shifting center of gravity, a shifting center of pressure, and how the forces from the canards can affect the flight of our rocket. We're also working on the design of our canard fins, where we want to place them, the size, and the length. If you're interested in any of this, let me know on Slack, and I'll teach you all about this.
Hey guys, I'm the ACS Electronics lead. So the progress we have so far is like Tispan was saying before, we're still in the preliminary design stage. So right now that just means that for electronics we're kind of we're in the stage where we're still choosing what electronics we want and what actuators. As of right now, we're gonna be using for sure an IMU altimeter and servo motors or motor depending on just our design. As of now, we're also looking into power draw, how we're going to disseminate the voltage between our components. We're also constructing the code, the Arduino code in C++, specifically for the IMU as of now. We also need to apply filters, which are a good way of mitigating the noise because our data can be inaccurate depending on just vibrational sensitivity of the rocket as it flies upward. And since we are still in that stage, we're hosting joint meetings with ACS controls. I mean, so as said before, we're using the main sensor we're going to be using is the IMU. It stands for Inertial Measurement Unit, meaning that it uses Newton's second law to calculate accelerometer and gyroscope data. And accelerometer, gyroscope, and magnetometers, those are just embedded sensors within the IMU, which gives us the position and orientation of the rocket. An IMU, for comparison, it's it's used nearly in nearly every application. It's in your smartphone, it's in gaming controllers, it's in cars, but this time we're strapping it into a rocket and we're getting important data from it. And this position and orientation data, we can turn it into aerodynamic characteristics, angle of attack, and coefficient of drag, which is very important for simulating the trajectory and just determining characteristics. And we can also record the flight trajectory, which for post-flight is going to be very, very important in terms of analyzing and just failure analysis. So if you guys are interested in electronics, just join the ACS meetings. We're going to be we're still in that design stage, but once we get further into it, then we're definitely going to be doing a lot more things electronics related.
So controls is really just the last step of making our control system. When we have the mechanical design and we have all the electronics, we need to figure out how we want to control them. So how will we control close the feedback loop? That's something we can discuss when we're there, but basically you just choose the gains so that your controller responds to the information your sensor sends you. So when we do controls, you're going to work on the control law for the ACS. And this will be using transfer functions. We'll probably put it in state space and in Simulink to simulate. And then once we're done with that, we can create a prototype to tune our control law. But right now, we're really just working on the design of the ACS in general. If you're in Mech E, controls and control lab are some classes you're going to take, and you can apply it in the subteam.
All right, can you guys hear me? Or no?
Yeah.
We can hear you.
Yeah.
There's an echo though.
You hear an echo?
Yeah.
You're echoing.
Okay.
Try clicking more and seeing if you have share sound and optimize for video clip in Zoom.
I'm going to try joining the audio on my phone because that might be
Okay.
better. Can you guys hear me better now?
Yeah.
All right. So, hi guys. My name is Matt, and I'm the lead for Flight Dynamics. So I'm just going to go over sort of what we've been working on recently on the team. So we've had a couple of meetings. A lot of it has been very theoretical, theory behind flight dynamics, but now we're really starting to put it all together and figure out how we put that into a simulation, specifically the MATLAB simulation. So there's really two separate things that we work on, two separate tools that Flight Dynamics uses. One of them is OpenRocket. So OpenRocket is a prepackaged software, very commonly used, proven and tested. So we basically build the model of our rocket in OpenRocket. So lay out all the components, lay out all the systems, get mass estimates, mass placements, center of gravity, center of pressure, and then figure out sort of through simulations how high the rocket will go, how fast it'll go, things like that. So some of the things we're working on now as the team is really refining that model. So as we get more information from the individual sub-teams, we'll have better mass estimates for those subsystems, better size estimates, and estimates for where they're going to be placed. So we're basically adding those to the OpenRocket model to make the model more accurate. The other way we can make the model more accurate is by adding more detailed components. So for an example, you can account for the parachutes in the rocket, and you can put the mass and the size of the parachute. But if you want to be more accurate, you can also include things like the parachute protector that goes with it, the quick links that go with it, the swivels that go with it. So these are ways that we can increase the accuracy of the simulation in small ways, but in the end could have a big impact on the predicted performance and how accurate it'll actually be. So on the other side, the MATLAB simulation, that's where we really code from scratch in MATLAB. We have a lot more freedom with that and a lot more ability to apply it more directly to our rocket. So what we're doing right now is we're reviewing the code as it is. improving its organization, seeing if there are any errors or if there are any approximations that we're making that aren't really valid, things like that. So that's sort of an overarching thing that we're doing. But one of the things that we have done, I guess, is we implemented a static stability margin check. So that was a recent addition, sort of just to see if the rocket is stable. It's a parameter that can kind of give you an idea of that. So another thing that we're working on is adding the ability to simulate 3 and 4 fin designs. So the simulation as it stands right now, it can simulate 4 fin designs very well, but we want to have the freedom in our design selection to choose either a 3 or a 4 fin design, for example. So it would be useful to simulate both. So the simulation right now can account very well for the normal force due to 3 or 4 fins, but we're working on helping it account better for how drag changes, whether it has 3 or 4 fins. And then the biggest project that we're going to be working on now is implementing pitch motion for the rocket. So right now the simulation accounts for a rocket that moves downrange. So you could think down the launch field, and also obviously up and down the altitude of the rocket. But a rocket is a rigid body, you know, it has a shape and it can rotate and things like that. So pitching is actually a super important motion for rockets. You can see in that visual in the lower right, sort of what pitching looks like. That can really affect the rocket's performance, its trajectory, things like how high it goes and things like that. So it's a very important effect that we're going to try to implement in the simulation. And that comes from understanding the equations of motion, understanding how you could implement that into an ODE solver in MATLAB, and just how we can make it better and optimize it and things like that. So please join my sub-team meetings every Monday, 6:30 to 7:30, if you're interested in working on this. Thank you, guys.
Hey guys, my name is Alex. Well, clearly from the beginning of the meeting, you guys know that, but I'm the Avionics Recovery lead for this year's IREC team. And for this meeting, I just wanted to go over a couple things that we have planned and a couple things that we've already gone over. In our first meeting that was last week, we went over standard methods of recovery with motor ejection. And an introduction to what dual deployment is. There you have 2 little pictures that were drawn during the meeting with the sub team. I couldn't fit them all in one slide to make them look big enough, but we'll go into detail in that later for whoever wants to join who's new. We also went over some methods of ejection within the recovery system listed there, CO2 canisters, which we're experimenting with. We're going to make design matrices to choose that later on. E-charges with black powder, which is the standard that we've been using so far, and piston ejection, which is something else that we've been contemplating, but it can be a little complicated on the mechanical side. For future meetings, I went over with the people that are currently on my sub team, and just like at the beginning of the meeting that we mentioned, within my sub team, we're going to be doing some general ed of rocketry and open rocket, because I think it's really important to have those essentials down packed, especially if you want to develop more as an engineer or whatever major that you have. It creates, you know, a bigger sense of understanding, because if you're kind of just in a sub team and don't know what's going on, then we don't want you to be lost, and you're never going to really grow and get to the point where, you know, you feel comfortable in the environment you're in. Later on, we're going to go deeply into failure analysis on previous launches, because in previous years, our rocket never really recovered properly. It kind of just hit the ground really hard and broke. In future meetings, I'm also planning to take that rocket to show you how messed up it got, because people tend to underestimate the amount of, like, you know, the difficulty that it is avionics and recovery, because like it seems like, oh, we're just deploying parachutes and stuff like that, you know, it's kind of like, you know, monotone in that sense, but no. We've actually had a really rough time trying to get the rocket back down, especially not only with this rocket but with certification launches, like using different methods of like opening the main parachute or the drogue parachute, like mentioned earlier by Bilal in those diagrams. Like, it's really difficult in terms of using like cable cutters, or something that we use called tender descenders that have a lot of failure points and that aren't really going to work because maybe a shock cord gets tangled, or maybe the parachute doesn't open because the parachute bag didn't get pulled off, and it's a lot of complicated things. So we would like a couple brains to help us critically think on how to organize something. For example, we have a recovery diagram that we have to lay out perfectly, And another good point that I have to make, just because we laid out a recovery diagram perfectly doesn't mean that it's going to go that way. So we're going to make a ton of decision matrices in terms of materials for shock cords, because depending on the ejection methods that we do, the shock cord might catch fire if we do it wrong. The ejection methods themselves are going to get the decision matrices, and we have to decide which one will be optimal for our rocket and our launch, depending on, of course, the simulation and our final design. As of right now, we're not 100% sure what we're going to go with in terms of recovery, because the open rocket simulation the open rocket model is kind of not finalized. So it might be dual deployment, or it might be some other type of recovery, having like 2 sections that come off with the different parachutes in different sections of the airframe, and the aft and the forward. So that's really, for now, what we have planned. Later on, we'll be testing hands-on with model rockets until we have something solidified with our bigger rocket to actually put to the test with ejection testing and stuff like that. So I encourage all of you to join my sub team. I think it's a really informative way and a really good way of introducing yourself, and getting rid of that intimidation factor that might come with like building a rocket or being part of such of a, let's say, open concept competition, because we are allowed creative freedom with a lot of stuff. So it's scary and intimidating. Sure, it might be hard, but we'll work with you to make sure that we get you to the point where you feel comfortable with the stuff that we're doing, and then maybe one day you could take over a sub team, or really contribute with your own ideas and your own progress. So another thing, I forgot to mention, since there's a picture there, that's a picture of an altimeter, because we're also going to be taking care of an avionics bay, where the electronics that measure barometric pressure, the height and stuff like that, so that we could properly eject our parachutes and stuff like that. So that's just a little example. Those are the ones that we used for certification flights over the summer and in previous rockets. So for now, that's all I got to say. Please join my sub-team meetings. They're from 4:30 to 5:30 on Tuesdays. This week, I couldn't do it on Tuesday for some family issues, but tomorrow we'll be having one in the late afternoon. So I'll keep you guys posted on my Slack channel, so be sure to join that.
All right, so for now, or for this presentation, we're just going to let Vishwak share his screen. He has a little demo to show us, so see.
I need permission.
You need permission? Okay, gotcha. All right, go ahead.
All right, there we go. Let me know when you guys can see my screen.
Yeah, we can.
All right, perfect. So this is my presentation on the telemetry sub-team that I've been working on for the past couple of weeks. So first of all, a quick introduction on why telemetry is needed. Well, a rocket is a pretty complex object. It's going in the air and we want to see information about it. Information is pretty vital to us to see what went wrong and what went right. And so with telemetry, we can see real-time data about the rocket, see if everything is going right, if the parachute is deploying right, and other vital information. We can also visualize this rocket information so we can see in real time where it's located laterally on like a map. We can see its altitude, its velocity, and if we wanted, we can put temperature on there as well if we wanted to. But that's kind of like a brief overview of why we need telemetry. So here's the setup for the telemetry in general. I don't know if you can see my mouse, but I'm kind of like going over the transmitter. So
Yeah,
the
we can.
Okay, perfect. So the transmitter is in the rocket and it's going up in the air, and it's being, and I'll go into like more of the details on how everything kind of works, but this is an overview. But it transmits information from various sensors back to a receiver on the ground. And that receiver is connected to a laptop. And on that laptop, there's this thing called Docker. Docker is kind of prevalent in like the CS world, I guess. And so it's basically just containers that run on your computer, which makes it easier to transport between different laptops if we need to on launch day. And so there's 3 different programs that's running on the laptop. There's the Python or Golang serial decoder, which takes the information from the Arduino, the receiver, and puts that into a thing called InfluxDB. So InfluxDB is like a time series database which is, I'll go into more detail on that as well, but it's basically just a database, think of it like that. And then Grafana is a data or dashboard tool that takes information from InfluxDB and presents it in a nice, easy to way to use. And so the transmitter and receiver setup is powered by 2 Arduino Nanos. I have a picture later on, but I can show that later. But it's powered by 2 Arduino Nanos, and the transceivers are actually LoRa 915 megahertz transceivers. And so the reason why this is being used is it's low bandwidth, meaning there's not much information. So it's not like we can't transmit like video information over these links, but we can transmit bits such as like altitude, the velocity, and other things like that. And so that's why the LoRa 915 megahertz transceivers are used. It's also very good for long distance, which is what we're going for. Since we're going to 10K feet, these would be perfect. And for now, we're just using spring antennas. And once we finalize everything, we can start testing and determine if we need to boost our antenna design or if we can get away with this design for now. And also everything is on perf boards, which I'll show in the later image, but we can start working on PCB design once everything is finalized. And PCB would be something like this. I don't know if you can see the screen or my camera, but it's basically like a board where you put all your sensors and stuff on. So we don't have to worry about wires like getting disconnected in flight. So right now, this is what it looks like. Of course, this is kind of like an MVP. There's going to be more sensors added on. And so on the left is the actual receiver. This is what's connected to the laptop. And on the right is what's in the rocket being getting information from various sensors and transmitting it down. So this little black PCB right here, the BMP388, is a barometer and a temperature sensor. So it gets barometer data and temperature data and transmits it to the Arduino Nano right here. And the Arduino Nano takes that information and sends it over the LoRa 915 megahertz transmitter, which sends it to this receiver right here, which goes to the Arduino Nano, which then goes to the computer, and etc. So the ground station is set up like this. I'll also give a demo on this at the end of the presentation, so this isn't too important to go into detail, but basically it's like the diagram I showed earlier. There's a serial decoder, which takes information from the Arduino and it puts it into InfluxDB. InfluxDB is really good for super quick reads and writes because it's meant for things like sensor data and like data centers, for example. It also has great support with Grafana, which is very good for making like graphs and real-time visualizations. And so here is what's done now. The transmitter and receiver base setup is finished. So we still need to put on like an enclosure. We definitely need to add more sensors. We need to do range tests to make sure like it can definitely go like that 10K feet and even beyond. We need to design the PCB and then manufacture it. We need to modify like some of the code to make sure that we're getting the best performance we can out of these transceivers. And on the base station, we need to account for the more sensors that we added. And we also need to maybe do some quick optimizations to make things run a little bit faster if we need to. And then we need to create the dashboard and make it look even better than it is right now. So who is this sub-team for? If you're interested in any of the things I've just talked about, if you're a computer science major, if you're an EE major, if you're a data science major, or really anyone interested in any of like the things I listed there, this team is for you, or this sub-team is for you. So if you're interested, join IREC Telemetry on Slack. I will send out a when to meet after this meeting, and then we can determine when we can have our meetings. And so now for a quick demo. So right now, this is, I'll unplug this at the end. I'll actually show this setup, but I don't want to unplug it right now because that'll kind of just mess this up. But what's going on here is I have a Python script running that's taking information from the Arduino through serial. It's communicating through the serial port. And so from that, it is getting all the information. So right now I'm just getting altitude and a thing called RSSI. That's basically like the signal strength. And that is being put into InfluxDB. So InfluxDB is this right here. I'm on InfluxDB right now. And so we can actually do like a query on different things. So we can do query on altitude and we can do 10 seconds or 1 second. and we can do like the past 5 minutes that it's been running. And so we can do pretty much all of that. And we can also see like on a table, for example. And the dashboards right now everything is on InfluxDB, so we still need to work on Grafana if we need to. If this is fine, then we can just use this. But I guess the problem is it only refreshes every 5 seconds, and there's really no way to change that. So we want to see real time, so we need to get that at least to like 1 second refresh. But this is kind of like a good overview of kind of like what's going to be on the ground station. So right now, this is the altitude. If I move the sensor up, I think it should pop up a little more. Yeah, so you saw that little jump right there. And it should also update here as well. So this also shows the RSSI value. So it's mentioned like dB or dBi or something like that. I don't know. That's basically like the signal strength. The closer it is to 0 or higher, or the higher it is, the better it is, basically. And so that's the overview of the dashboard. There's also things like alerts we can set up. So I set up this quick RSSI health check, so we can see. So we can have like alerts set up. So if the RSSI value goes below like -100, which is pretty bad, I guess, then we just say, hey, this is critical area, and like the person on the ground station knows that we're about to lose like contact with the rocket, or the telemetry at least. And I think that's pretty much it for IREC telemetry. Yeah, so
Thanks, Vishal.
yeah. So join the Slack channel and fill out the link to meet.
Yeah, thanks, Mishbach. Then I can share my screen from here. We're back on the telemetry side. All right, cool. So next is the payload team. I'll let Christian take this over.
What's up, guys? I'm Christian. Can y'all hear me?
Yeah.
All right, sweet. So I'm one of the only payload lead right now. I'm the payload mechanical lead. And basically, this is our newest sub team on IREC. So we're kind of still in the beginning stages of our work. You know, like Bilal described before, we're basically launching a payload that contains some cool technical science experiment. And we're supposed to set it up in the form of a CubeSat, not like an actual satellite, but kind of framed similar to how a CubeSat would be. And again, we're still looking for that payload experimental lead. You know, we're making a little progress on figuring out our experiment, but nothing's set in stone yet. So we still want those applications. Feel free to talk to me or Bilal if you have questions on that. On my end, I'm working on the mechanical subteam for the payload. So we're basically working on designing the frame and mounting for different configurations for a payload depending on what our experiment ends up being. You know, like if the payload is just going to stay in the fuselage of the rocket the whole time. If, like Bilal mentioned, the payload's going to be attached to the parachute line of the rocket and eject on that parachute, or if it's going to eject on its own parachute out of the rocket. So we're just kind of ideating on that right now. And we're making some progress on that. But again, you know, we don't have our experiment yet. So anything could change, and ideas are still very much welcome. And we're going to need people to help us, you know, with some SolidWorks for the frame and probably the mounting as well. So if you know that skill, that will be very good for us. This will be a very good sub-team for you if you like CAD and whatnot. You know, we're also going to be running some higher level simulations on SolidWorks, some FEA, which if you don't know what that is, it's basically a way to simulate the stresses on the structure of the payload to ensure that it's structurally sound. So that'll be another cool thing to do, new skill to learn, whatnot. And of course, we're going to be building this thing from the ground up and integrating into the rocket. We're going to be testing it during flight, see how it works, how it holds up, how our experiment when it have it holds up as well. So yeah, we meet twice a week for the mechanical team. We meet Mondays at 6:30 and Fridays at 4. So our next meeting will be this Friday afternoon. This one will be on Zoom for the time being. But yeah, if you have any questions, feel free to Slack DM me. My name is obviously under my face, and feel free to reach out if you want my number or anything like that. So yeah, thanks guys. Join Payloads.
All right, so next we have the structures team. The structures lead couldn't be here, so I'll just present for him today. We're designing the BTPJ, which is a airframe, a precision airframe rig, basically to make slots or cuts into the airframe. It's pictured on the side. Josh, do you want to give a little bit more of an overview on the BTPJ?
Absolutely. And for those of you who haven't heard of me from the first GBM, you'll see in a slide later, I'm Josh, the manufacturing lead for IREC. So the BTPJ stands for Body Tube Processing Jig. As the name implies, the rocket's body tubes are mounted between the two large cones on either end, which can rotate, as you see in the image. Additionally, a Dremel will be mounted on the carriage assembly you see in front of the body tube, that cylindrical portion, which can be positioned in two axes like on a manual lathe, like we have in lab, to cut into the tube. Ultimately, like Bilal said, the BTPJ will be used to make cuts that are very accurate and repeatable for the entire team.
Thanks, Josh. So I think it's a great, the BTPJ is a great project to start on. If any of you have any experience with SolidWorks CAD along with the payload. It's also a project I'm really looking forward to coming to fruition pretty soon, actually. We're going to get started on the manufacturing. It's going to be our first like manufacturing project, essentially. So pretty excited for that and the help it can give us for building certs. So also, in addition to the BTPJ, the structures team is working on a modular fin and aft system. What that means is essentially a way to have the fins be able to come off and on, kind of like a Lego piece on our rocket. That's very useful for a rocketry team that wants to do a lot of launches, because of all parts on the rocket that's going to break, it's probably the fins when they come down and hit the ground. So it's an easy way to just make it plug and play and really have a good system. On the horizon, we're also going to be doing carbon fiber layup of the body tubes. So we want a whole carbon fiber layup or a carbon fiber rocket. And we're going to start developing our design for manufacturing of the modular fin system so that so we can hand it off to the manufacturing team for production. We're also going to be designing molds to be CNC machined for composite manufacturing, similar to for the carbon fiber manufacturing. And we're going to start prototyping and testing that modular fin system once it's ready to go. I'll hand it off back to Josh.
Alrighty, back to me. This is just a slide I repeated from the first GBM. Hi again, I'm Josh, the IREC manufacturing lead. Here just is a list of some of the things I do. And then of course the pictures to the right, hobbies and things, very fun stuff. You can move on to the next slide. So manufacturing, our progress so far, as you've been hearing, is we've been in collaboration with structures working on the BTPJ. Off to the right, manufacturing in particular, our sub-team has been responsible for designing the Dremel carriage. So that's depicted in the top right. So the Dremel is inserted in between the two portions of the clamp on top, and it can slide in and out towards and away from the body tube, and left to right longitudinally along a piece of NE20. Yes, like that, as Bilal is showing. And so additionally, we've been with a few sub-team members going through a brief introduction to our lab facilities. The pictures you see below are of our essentially the DML lab, if any of you have taken DML, and the Mech Design 3 lab. So Mech Design 3 on the very left, DML in the middle. And then within the Mech Design 3, we have a row of 3D printers that we'll be using to iterate some components for the BTPJ. Moving on. So upcoming, I'm going to send out a feeler in Slack pretty soon, but we're going to try and get as many people as possible machine safety trained so that we can actually start deferring component manufacturing so that the DMLTAs like myself aren't the only ones who are going to be responsible, since not all of us are dedicated to the manufacturing sub-team for IREC. Furthermore, we're going to be discussing some basic DFM and DFA. As Bilal mentioned briefly, DFM is designed for manufacturing and DFA is designed for assembly. So some basic concepts for those to make sure we implement those good practices in what we're designing. And then finally, like I said, with the 3D printers, we'll be prototyping some of the components very soon. Overall goals, I would like to get more people trained in more advanced manufacturing techniques. So that includes more than just watching me do it. So actually people understanding how to use the CNC, how to use like the abrasive water jet, and doing more than just some basic passes on any of the milling or lathe machines we have in lab. And then of course, some other projects, the modular fins, as said before, and then in a little bit, Oz will talk about the propulsion side of things, and we might get tasked with designing, or not designing, but rather manufacturing a propulsion testing stand. So that's it. And then off to the right, the top figure is from our SDC lab. And then the bottom is the water jet room, the machine right in the middle. So that's the end of the slides for me. If you have any questions, feel free and don't hesitate to message me in Slack, or at any time, contact me after the meeting, and look out for meeting announcements and that feeler message for safety training so we can gauge how many people actually want to go through that. Thank you guys very much.
So also our propulsion lead couldn't make it today, but and I'll be presenting for him. So under propulsion, we're just getting started on doing propulsion for the first time ever in Swamp Launch history. So still very much in the beginning stage, still learning a lot. We're first going to start on just designing a test bench, not even touching motors yet, to conduct motor testing, mainly getting a thrust curve, thrust versus time, and focusing on safety so we can really convince the administration that they should not cancel us because we're making bombs. So that's really important. Looking to begin work on sugar motors. So the real rocketry motors that we use are made out of a chemical called ammonium perchlorate, which is not super crazy, but it's more I guess like professional and more combustive type of substance. So instead of starting with that, we're going to start with sugar motor, which is sugar, making motors out of sugar, which is pretty simple. You can do it on a pan. In fact, our mentor, Jimmy Yan, has showed us a lot of techniques that he's developed himself. And they can make a pretty good motor, about 70% of the effectiveness of an AP. Starting on lower motors and then building our way up until we can actually be confident in flying one of these motors on a cert rocket. And then if possible, we'll start stepping up to eventually H's and so on. The goal isn't necessarily to make a motor immediately for IREC, just to get our propulsion team started so that in a future launch or a future team can start using M motors that they made themselves. Meetings will be announced next week on Slack, so definitely join the propulsion sub-team channel on there to get any updates. So in addition to the, or carrying on from what payloads was, from what Christian was talking about on payloads, the Space Dynamics Laboratory runs a payload competition within IREC. It's basically that experimental payload that we've been talking about. The task is to make an experimental payload in the CubeSat format, and the experiment is entirely up to you. This is an open lead position, essentially, that we're trying to find a really good member to work on. The technical requirements is that the system must be greater than 8.8 pounds, but a lot of that can be in the whole payload structure as well, so not really a requirement for your experiment. It must be in the CubeSat format. and it can be ejected from the rocket, just like as we've discussed. So we're looking for a lead to conduct an experiment on our payload. It could be pretty much anything like we've said before, biological, physics, meteorological, whatever you desire, I guess. And we're also open to pretty much any of your ideas. So if you have an idea, or if you want to become a lead on the team, please sign up for that form on the Slack. We're pretty much just open to ideas to conduct an experiment on right now. We're also looking to collaborate with the SSDC Space Systems Design Club on building or adapting their payload to our IREC payload. So if that sounds interesting to you and you're looking for a lead position on a team, please check out the sign up form on the Slack, and I'll send another announcement after this GBM. And finally, if you want to keep in contact with us, our Slack, Facebook, Instagram, and Twitter are listed on the page. I think you guys are all on Slack, so I think that's all good. But if you aren't already, join our Slack. But yeah, that'll conclude it for today's meeting. If you guys have any questions for the leads or me, the remaining of the time is for you. So if not, we'll close it out here.
Yeah, thanks for coming, guys. Just as a reminder, meeting next week will be a general education meeting hosted by Alex. So it'll just go over the basics of rocketry and anything you need to know. So hopefully, if you had any questions about rocketry or like what we do as a club, we'll be holding these meetings from time to time to help answer those questions and help develop your knowledge and fill in any gaps that you might have.
Don't be scared to stop by.
I got one question. Is there a Propulsion sub-team Slack channel? Yeah, there is. If you go on Slack and you press the plus sign next to the channels tab on the left, you'll see it says browse channels, and you're able to search up all the channels on there. Maybe I can stream that real quick. Right, so if you go onto the channels tab here and you press the plus sign, you'll have this whole browser of channels that you can join. There's a ton listed here, so you may not be in it automatically. So right, and if there's not any more questions, we'll just close it out here. Thanks for coming, guys.
Swampo?
For sure, yeah.
Have a good one.
Bye.